Okay, so now let's talk about electric potential energy. Electric potential energy. Here, if I get a question like this, I could be asking, what is the electric potential energy, or the total, or I could be asking, what is the potential at some point? Let's do both. The electric potential. Let's do both. For the electric potential, we'll choose like a point here. Let's just start with potential energy of the system. Okay. For potential energy, what did we have? We had that, let's see, I think I have it right here. We defined the potential energy as being the potential times Q. Bring that on over. Oops. That is our potential energy. There shouldn't be a negative sign there. Just want to make sure that's clear. And what does it mean for something to be scalar? Just a reminder, now it is okay to use the signs on the charges because these are scalars. The one thing I didn't show you that is in the book is that part of what we do in the math in the background here is a dot product. So remember, the dot product between two vectors creates a scalar quantity. So the integral we're actually doing is the integral of the electric field dotted with that distance. That's why it's a scalar. And we know that potential we've defined as being kq over r. So we have this q and then we have this q. How on earth are we going to apply that to figure out what the potential energy of this system is, and what r am I looking at? Well, what you're looking at is the interaction between each of these charges and each other. So I'm going to have one that is this. This would be, let's go ahead and label these as charge 1, 2, and 3. So this would be like Q1. I don't want that. I wanted a pen. Q1 interacting with Q2. And then like this line here would be Q3 interacting with Q2. So I have 3 interacting with 2 and 1 interacting with 2. The only one I'm missing then would be like this straight line happening here. That's more or less a straight line. And this would be between 3, so Q3 and Q1. I have told you that 2 of them are positive and 1 of them is negative. So my potential energy for this system then is going to be the potential of each. So that I can't forget my K. This is going to be like my KQ over R times the Q I'm interacting with. And I want a sum of this thing. So the sum of this thing is going to go to, let's see, I can pull out my K. And I can say, okay, Q1 times Q2, just starting with this one right here, over that distance R, which is now just L. Let's see, Q1 and Q2 are positive, so that's a positive. And then I'm going to go plus, now Q2 to Q3 interacting. So Q2 times negative Q3 over that distance. And then plus Q1 interacting with Q3. So Q1 times negative Q3 divided by that distance. Well, that distance, that's Pythagorean, so the a squared plus b squared, so L squared plus L squared, so 2L squared. And now we're not squaring the r, so the one thing you want to be careful of here is I'm going to have 2L squared. I can pull the L out, and I'll have over the square root of 2. So this thing then is just going to simplify down to k times, they're all the same magnitude, q squared over L minus q squared, whoops, squared, not a subscript, minus q squared over L. What? Yep. And then minus q squared over L times the square root of 2. So I look at this, and then I get all happy. That cancels, that cancels. So this is going to go to, we can pull the negative out, negative kq over L root 2. Now, one of the things I've been talking to everybody about is learning to simplify things as much as possible, and y'all are doing a fantastic job. But let's go ahead and do that now. The way I do that is multiply the top and bottom by the square root of 2. I'm multiplying by 1, so I'm not changing the expression at all. So this is going to simplify even further to negative k q, not a g, root 2 over 4L. I'm sorry, 2L. Ooh, I can't do math in my head. So root 2 times 2, root 2 is 2 over 2L. And that's it. That gives me the potential energy at that point. If I want to look at the change in it, well, I don't really have anything to compare it to. So I'm not looking for a change in potential. That just gives me the overall potential. And we could look at this, we can look at it in terms of our electric fields. Let's see, these two things, it shouldn't be too much of a surprise if I go back to my vector quantities. Same distance, same magnitude away, so those x components are going to cancel. What happened there? Something canceled. And what do I have? I'm left with something coming like this. So this positive, I'm sorry, yeah, going into here. And then I'm accidentally doing forces, so we'll stick with forces. So I'm going to have a vector going this way and a vector going that way as far as my forces go. So it can come up here to my dot on Q1. These two forces cancel. I'm going to be left with a force that comes like this and a force that goes like this. And add those two things together, and if you've done enough practice with your vector quantities, you can kind of deduce where the resultant is going to come. But it's going to be out like this way. Okay, that gives me like the net force between those things and the force over the distance that the forces are happening. Well, what do we end up with? We can look at that is going to be the energy. So if I wanted to turn energy into force, what could I do? Oops, I dropped a squared. Think that over, and let's talk about it Wednesday. So if I wanted to turn this and go back to forces, where could I go? But see, as far as potentials, oh, I didn't answer the potential part. Yeah, I just went with potential energy. So the potential part, what's going to happen there, if I want this point here, ooh, do I want to make that a next video? How long is this? 8 minutes, we're good. Okay, so for doing the potential, I'm going to do this over here. Why am I chuckling? Because I inadvertently made my life not an easy distance. So what do I need? I need the distance from here. So I need this guy. So this would be like 1/2 L. I can look at this. Yeah, I'm just going to say I chose a spot midway, so this is also 1/2 L. Because I can do that, I just made the question up. And then the distance from here to here, well, this is going to be the exact same distance, so this is also going to be 1/2 L. And then the same hypotenuse. And then the distance from here to here, what can I do? I can make this triangle, which is going to have, whew, made life a little bit easier for myself. Bunch of those. So what am I going to have? Let's just kind of scratch this out because they're all going to be equidistant from that point because that's how I was nice to myself. So L over 2 squared plus L over 2 squared. Let's see, that's going to give me L squared over 4, 2L squared over 4. I'm taking the square root of that thing. So I can simplify it in there. Yeah, let's do that. So my distance away is going to be L over the square root of 2. The 2 and the 4 simplify to L over 2. There's my square root of 2. That's my R. All of them have the same R. So V equals, let's see, K, and then Q, didn't I write that down? Here's my potential, KQ over R. Just like my potential energy, I'm going to add everything and use the signs. So when I do that, let's see, for charge 1, it's a positive Q1 divided by L over the square root of 2. And then let's see, plus the other positive Q2, same distance L over the square root of 2. And then minus that third, Q3 over L over the square root of 2. Cool. And just like what happened before, Q1, Q2, and Q3 all same magnitude, just two of them have different signs. So one of those are going to cancel, doesn't matter which. And then I'm left with this. And let's simplify this so it's not this ugly thing. So I'll have KQ1. I have a fraction on the bottom of a fraction. What does that mean? So I have literally L over the square root of 2 written down below there. I just kind of put it at a slant. So if a fraction lives on the bottom of a fraction, I just flip this thing. So I'll end up with the square root of 2 over L. So K, Q, root 2 over L. That would be my final, not a V for velocity. Sorry, velocity too long. V for potential. I'm going to erase that so it's not confusing. So how do these two things compare? So I have K root 2 over L, and this thing here, I have K, Q, root 2, but there's an extra Q, and there's a 2L. So how do those compare? Why are they slightly different? Well, so they're going to be slightly different because the distance, right? So I chose a different point. In the first one, we did the overall charges distributed. In the second one, I picked a point, and I said here. Now, if I wanted to know the potential energy at that point, that would kind of change things, wouldn't it? I don't know that that would actually make sense, because you'd be doing the overall potential energy of the system. At any rate, so the potential for our points interacting, then we end up with this KQ2 over L. And then we have the addition of the additional charge interacting with, because remember, all potential energy is Q interacting with potential at that point. So actually we could, if I wanted the potential at this point, it would just be times the Q. Okay, so the big difference there, this is my point here. This is for the system. And this is for point, I don't know, whatever that point is, some chosen location. All right, I think that's good enough.